I want to look at last year's Black Friday, minute by minute by minute, to understand what the users were doing and how our systems behaved, so that when I prepare for this year's Black Friday, that I'm not screwed. I want to know that data. So, how do you do that? Well, when you want to collect 1 trillion things, you don't use one machine. And when you want to store 1 trillion things, or 1,000,000 trillion things, you don't use one machine. So our architecture is actually very straightforward. So we have collection nodes at the top. Those are all an open source product called Reconnoiter, and it basically knows how to speak different protocols. It talks SNMP, it talks JDBC, it talks HTTP. It can read JSON documents and XML documents, and it pulls numbers out of them. So basically, it's collecting things like how many transactions you're doing per second, what's the latency on each disk IOP, all of that kind of stuff. It can collect that data. That all funnels into our system across an aggregation layer, which runs many nodes. And then that's where it gets somewhat interesting. So one part of that aggregation layer spits everything down to a storage layer. We originally built this on Postgres, and I'll talk about how that was a great idea that failed. And we also send all of the data in real time to a message queue. And we originally built that on RabbitMQ, which was a great idea that failed. So I'll walk through both of those. So distributed collection, like I said, we use Reconnoiter. It's open source. It's BSD licensed. It is by design distributed. It's designed to collect trillions of measurements a day. It's hard to collect that on a single node, so it's distributed. The jobs are run, so basically a transaction will happen, whatever that is. Maybe a web request to get a JSON document, maybe an SQL query to get transaction volume. Maybe you're running dtrace or KTAP on your Linux box and giving us every single latency of every IOP. And that goes in, and we take that data and we put it into a Google protobuf, and we shoot it across SSL back to our big brain, and we push that through disk. So those boxes, they store all of that through a disk journal, so that if you disconnect, if that node that's collecting data out in the world has a network partition, it can continue to collect its data, and then it will eventually stream it back up. So it's a store and forward sort of thing. And we'll get into why that sort of matters in a second. Aggregation, it turns out that you can go very, very far on a single node for aggregation. All it's doing is putting things into storage and putting things onto an MQ. The idea of routing billions or trillions of messages a day is actually really easy. Turns out that doing that on RabbitMQ was really hard. So redundancy was simple, scale out was not. We solved that problem, but I'm not going to talk about that too much. So storage. So kind of half of this talk will be about scaling storage, and the other half will be about scaling MQ. Postgres, great database. We still use Postgres. It is the core metadata database for our system. We have hundreds of tables. We have extremely complicated queries, queries that are 16 kilobytes long with 40 joins in them and things like that. And it's fantastic. It runs fast. When we put time series data into it, the way we had to operate that system changed. And that data is inherently not relational, which is one way to think about why a relational database is not ideal. So, boop. 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 Next slide. Technical difficulty. There it is. Wow, that went fast. Nope. That was a lot. All right. So the first thing that we did in Postgres is that we had a table that had a timestamp and a value, which sort of makes sense if you're storing time series data. And we put that in there. And the problem is that every single measurement has this data point name in it. It has a timestamp in it. Those timestamps tend to be very regular, but we don't capitalize on that. So it takes a tremendous amount of storage space. So the first thing that we did was we decided that we would store data minute by minute, and there are 1,440 minutes in a day. So what we did is we took, instead of having 1,440 rows in our table, we had one row where one of the columns there was an array of 1,440 integers or numbers. And then we would update that row and just offset into that. And due to some of the properties in Postgres, the indexes never had to be updated because we didn't index on the array, we indexed on the timestamp. So that actually went very, very well. We got a reduction in storage space of about 30-fold. That was fantastic. There was one row per day per data item. But the real problem that we had was that as we grew, at our current architectural scale, we would have probably approaching about a petabyte of data in Postgres. And if you've ever run a relational database, rule 1, don't put a petabyte of data in a database. What we had was we had this thing federated and sharded out, but each one needed a failover, so we had pairs of nodes, master and slave.
И всегда была основной, вспомогательной,
nodes, you're going to have a failure once every 2 weeks or so. And rebuilding those slaves took a tremendous amount of time. So it would take an hour of time for an operator to go in, promote the slave to master, destroy the old master, or reboot a new master, blank it out, make a new copy, and make it the slave. That was an operator action. Even if it was scripted, it required someone's attention, and it was kind of a pain in the ass. So what we really wanted was a system that did all of that magic by itself. So I have a background in distributed systems. I've built some databases before. And rule 1 is don't ever build your own database. But we had a very special, unique case here. And we needed to reduce the management burden. We needed to reduce the management burden. But the most important thing about building your own database is that you don't trust your own database. So we needed to run Postgres and our new solution at the same time, because a horrible idea is to decide that on November 4th, I'm going to switch databases. Never works, right? You switch databases, it all explodes, you have to fall back. Databases in particular, it's very hard to fail forward with databases. Because you have new data coming in. It's stored, it may be in data models that don't exist in the old system, and then when you fail back to that old system, you have to be able to pull the new data and put it in the old system. It's a disaster. So you always want to do concurrent operations if you can. So we built a system called Snow. It is very DynamoDB inspired. The reason that we decided to do this instead of using Cassandra or React or any of the other databases out there is that every single operation we do on our database is commutative and idempotent. I don't have to worry about adding dollars to your bank account. That's not how our system works. And all of the complicated technology, all of the really hard problems in distributed database design are about people agreeing. And if your operations are idempotent and commutative, you just have to do it. You don't have to agree to do it. So everyone can do it, and if I get a copy of that, I can do it out of order. As long as I apply all the same transactions, I don't have to agree on their ordering. I don't have to agree that I can only do them once. I'll end up with the same answer. So it's much easier to build an eventually consistent system if you can prove commutative operations on all your data types. So, how does our system look? We have a ring. So this ring is actually 256 bits, right? So it's a 256-bit clock. So the number of little ticks on the clock is 2 to the 256th. In this example, we have 6 nodes, N1 through N6, they're color-coded. And what we do is we take the node and we hash it using SHA-256. So we get a 256-bit hash out of that. And that hash will describe where the node lives on the ring. So you would think, why aren't there only 6 of these little nodes? Well, it turns out that if you take 6 nodes and you hash them, they will not at all be evenly distributed on the ring. And what we want is a more even distribution on the ring. So we increase our odds by making virtual nodes. So node 1 will have, in this case it has node 1 through node 1 ABCD. Here it's node 1, 1, node 1, 2. So you can see this is node 1, 1, this is node 1, 2, this is node 1, 3, this is node 1, 4. The idea is that they will be more evenly distributed and have more ring coverage. They are all the same node. They're just kind of different ideas of that node. So you hash all of those onto the ring, and then you want to put a piece of data in the ring. Well, you have a piece of data, and you have a key for that data. You hash that to a 256-bit hash. It identifies a spot on the ring. So my data lives here. Well, so the interesting part of your data living there is there's no node there. So what we do is we walk clockwise around the circle. And if we have 3 copies, by default we have 3 copies of data. We can configure that for 2 or 4 or what have you. But we hit node 6 first, then we hit node 3, then we hit node 6 again. We already saw node 6, so we ignored that, and then we hit node 4. So I know that the 3 copies of my data live on those 3 nodes. It's fairly straightforward. So this has the unique property that's talked about in the Dynamo paper, is that if I remove a node or add a new node in, that the keys, all of the data that sat on other nodes, there will only be 1 over k redistribution, right? So each node will really only lose 1 over k of its data, because things don't move. Like node 6 is always where it is on that ring. So if I add a node 7, it will only steal the keys for things where it kind of sits in between other nodes. Which means that when I add a new node, I have a minimal redistribution of data. So it makes it a lot easier to add a new node or remove a node. So much different than federating data or sharding it. So we have a problem in this. So what happens in real life, this looks good in practice, in theory, but in real life I have, say, 2 racks of equipment, and the most common case is not a server failing. They don't actually fail that often, and once a server fails and you survive, everything seems like it'll be great. You have a PDU failure, so power fails in the whole cabinet, or you have a top of rack switch failure, so now none of the nodes can talk to each other in that rack. So what happens when those 3 nodes happen to be in the same rack? There's no way to deal with that. So what we did is we had this idea, what if I could split the ring in half? Well, clearly that won't work, right? Because I have node 1 on this side and node 1 on this side. It can't be in both places at the same time. So what we do is that 256-bit hash, we save 1 bit off of the end. And we reserve that bit for the side of the ring that you're on. So it rehashes things slightly. So if you start this way, node 4, 2, and 6 are on the right side, and node 5, 3, and 1 are on the left side. So now, we just have to change the way we walk around the clock a little bit. So when a node comes in, we walk clockwise to the first node, and then we move pi across the ring. We move 180 degrees around the ring, and then we walk a little bit more. So we walk down, find a node, then we walk over, we find a node, and then we walk back and we find a node. And we keep doing that. And that way you can always guarantee that you have at least 1 on the other side. You'll have basically half of your nodes in each availability zone. That way when you lose a cabinet or you lose a switch, everything's fine. Everything goes on. So it turns out that this is really easy to build, but what we end up doing is actually just running 2 rings. It's easier for people to understand. So we built that technology, and people really like it, and nobody uses it, turns out. So keep it simple, stupid. So this is what a real ring looks like. So this is a 6-node ring. When you saw the little 4 surrogate nodes, we usually use many more than 4. This one has 85 surrogate nodes, so the weight here. So each node, this node right here, actually has little 85 copies of itself all around the ring. And you can see that as you increase that number, the distribution, this is the coverage, are relatively equal, right? The lowest one has about 13% of the ring covered, and the biggest has 20% of the ring. So they're not perfect, but they're very good. So the most important part of this was that we didn't have to solve agreement protocol problems. We didn't have to use Lamport timestamps. We didn't have to use vector clocks. We didn't have to do leader election algorithms. We didn't have to do any of that because all of our data was commutative. So this whole product took about 3 months of one engineer to build. It was very, very straightforward. And this is what our growth looks like. So this is why we have an exponential curve, which is why we wanted to switch technologies, because this is what our Postgres database looked like. This was us growing out of control and then deleting a whole bunch of data and growing and compacting and then growing and being, oh shit, and then growing again. And the interesting part, the takeaway from all of this, why this is so important, is because these things overlap by 9 months. We were running the same system and putting all of the data into both systems for 9 months, and we were able to flip users back and forth between those systems for reads, and they didn't know. And that was the beauty of that, is that we built this here, and then right around this line, we started putting all of our internal customers on the new data store, and they would complain that the standard deviations were broken, or this math was broken, or this average doesn't look right. And we would debug and debug and debug. And then somewhere around October here, we actually flipped all customers onto this. And then we turned the database off here. We'd forgotten that it was still on, because that was like 3.5 months there. And then right around here, we got some complaints from users that they thought data was wrong because they had just been flipped to the new database. So it's really interesting how your users can have no idea what's going on if you do things correctly. So this turned out to be very, very low maintenance. So anytime a node fails, nobody cares. There's 2 other copies of the data. When the node comes back up, all of the transactions that were stored for it flow back in. It doesn't have to worry about ordering. Everything is actually very, very simple. It's very easy to reason about the database and how it works. So if you ever think that you want to build your own database, answer one question, which is, can I reason about how it's not working? And if you say no, use someone else's database, because they spend a lot of time reasoning about how the database works. But if it's very, very simple, like a key value store, like Redis or something like that, the concepts behind that are very, very simple, until you try to do distributed Redis, which doesn't even work very well. So don't use distributed Redis. So single node key value stores are very simple. So building your own isn't that scary. Building your own relational database is a very hard problem. Building your own distributed system is kind of a hard problem. So the most important part of this is that the time and safety aspect of that is that we took 9 months of running both systems at the same time, and that was safe. So the next thing that was really interesting is that if you went earlier, Bruce Momjian talked about how awesome Postgres is, and Postgres is awesome. And you can embed R in Postgres to do statistical processing. Well, it turns out that if you store your data as efficiently as we do, it actually makes a lot of sense to embed something like R in the database itself. So what we did is we took LuaJIT, so the Lua language. We wrapped it around all of the same math libraries that R uses, all of those old ones from the 1970s and 80s written in Fortran for probability distribution functions, random functions, LAPACK, LAS, all of those. We wrapped those in Lua, and we exposed those in the database so that when someone wants to crunch 1 trillion data points, they can send their computation into the database and it can run right alongside the data so that you don't have to move 1 trillion data points out over the network, crunch them, and then do something with them. So it turns out that some things, like calculating a 99th percentile across 1 trillion points, very easy to do if the data is right with you, very expensive if you move 1 trillion points across. Other things, like calculating a Markov model of data movement, very, very expensive, not very much data. Maybe it makes more sense to pull the data out and do your Markov model outside and give the answer. So what we did is we built a hybrid system where you can either move computation to data or you can move data to computation. And that turned out really, really well. So that was exciting. So we have this system that can answer and draw graphs, and that's beautiful. But people also want to know when things break. Right? So when I have data that doesn't look correct, how do I detect that? And the answer is I want to know now when the data is broken. I don't want to know in 5 minutes or in 20 minutes or next day. So this system has very different semantics around real-time data. So our real-time requirements are soft real-time requirements. Our requirements, so when you think of hard real-time systems, there's a difference between soft real-time and hard real-time. So soft real-time, both of those have a deadline. So I need to do some computation, I need to answer a question, and I need to answer it in 20 milliseconds. So soft real-time systems are, if I don't get all of my inputs and can't produce an output within 10 milliseconds, it's not worth as much. In a hard real-time system, it's not worth anything at all. And usually people think of hard real-time systems as control systems for cars and for planes and things like that when, you know, if you have turbulence and the rudders need to go up or down and they don't do it on time, you crash and everyone dies. Those are hard real-time systems. But our system actually is a hard real-time system as well, because if our data doesn't show up within 10 seconds, it is not worth anything at all. We actually throw it away. So the storage system keeps it all, but this system actually throws away old data. So what happens is we have these Google protobufs coming in with all of our metrics. And we take each of those metrics and we put it over an MQ so that processes can read them and make smart decisions on them. So RabbitMQ, we had some experience with, we started using that. And things worked very, very well. We really liked the product. We actually still use the product. But they broke badly. And the first reason they broke badly was absolutely our fault. If you have a message queue that you're using for data, and you're also using it for control messages, you're an idiot. I was an idiot. So never put control data on the data plane. Right? They never put data on the control plane, right? You can't mix those two things. So the first thing that we did to solve our problem is we made 2 RabbitMQ instances, one of them for control messages, which are always rather low volume. And all of our experiences with RabbitMQ not working correctly are at high volume. So once we split them, the control plane always worked. It worked well. And then the data plane would crash and burn and explode and take other systems with it. It was very bad. So what we realized after the fact was that all of the benchmarks that we had been using from RabbitMQ, they used 0 size messages. Turns out our messages are not 0 bytes long. Yours are probably not 0 bytes long either. So that was one of those what the fuck moments. And we reran the benchmarks, and what we found were all of the behaviors that we saw in production of the system becoming unresponsive. In our system, we send at times up to about 2.5 million messages per second. Those messages can be anywhere between 200 bytes and 6K. And when you think about that and you do the math, so for example, one of our processes is a Java process that does all sorts of math on that. If it goes into a garbage collection cycle and takes 1 second, right, it pauses for 1 second and doesn't read off of the queue, you now have 2.5 million 6K messages in the queue. That's not small, right? And it turns out for Rabbit, that's huge. Rabbit's like, that's a lot of messages, right? Whereas for us, it's like that was 1 second of pause. So in some of the higher bandwidth systems that our clients run, you can see up to 4 or 5 million messages a second, and some of them are bigger than 6K, and now suddenly you're talking about gigabits and gigabits that just flood into the queue every second. So RabbitMQ seemed less and less ideal as a solution. So we went and failed it. So one of the biggest problems that we had with it is that when we sent a lot of data, it didn't just break. It went off the reservation. It started acting crazy. Some messages would pass, it would say everything was okay, you couldn't connect. It had very, very odd behavior as it tried to stay up, but clearly couldn't do its job. All of the stuff that we did with RabbitMQ, our stuff is running 2.8x, 2.82, 2.83 maybe. There are some improvements in 3.0, particularly around benchmarking. But in the end, if you're sending incredibly high message volumes that are PubSub, it may not be the right choice. We still use RabbitMQ for our entire control plane, and it works great. So we looked at a lot of solutions. We looked at primarily Kafka. Kafka was early on in that, and we didn't quite trust it yet. And today, I think we still wouldn't use Kafka, not because it's a bad product, it's mostly because we don't have a lot of low-level systems Java expertise. We're all good at writing Java apps that process stuff in user space, but Kafka has to run 24/7 with no interruptions, no garbage collection hiccups. It can't pause for 10 milliseconds. Can't do any of that. So there are some operational challenges with running Kafka, and the other thing is that it requires Zookeeper, and fuck Zookeeper, right? We do not have Zookeeper in our architecture today. If we did, it wouldn't be a big deal, but I do not want to introduce a new complication that is Zookeeper. So we looked around, and there is a rule that every general purpose solution will never be as good as the single purpose solution you build. So we built FQ, which is on GitHub, it's BSD licensed as well. And FQ stands for fucking queues, of course, because you're angry. Always write system software in anger, always. Comes from the soul then. So, there we go. So, FQ. So we had some basic concepts around FQ. We wanted to support two models. One is dedicated queues where I get a copy of every message. We wanted other queues where consumers could compete. So myself and 10 other jobs could compete to drain the messages, where we would kind of round robin across all of them and we could drain the queue faster. So one of them is for telemetry data, where everyone who's watching needs a copy of all of it. And the other is for kind of job dispatch, where I put 50 jobs on the queue and then, 10 consumers can pull off 5 each. So we wanted that. Another really important semantic that we wanted is we wanted the user that's subscribing to be able to control the flow control of that. So the last thing I want is I like to give our developers access to production, because that's where they learn all of their valuable lessons. So when they connect to production, the last thing I want is for them to break the system unintentionally. So in most message queuing systems, not all, but many, when you connect and you read too slowly, you can have a very negative impact on all of the publishers. You can start to slow them down. And in our system, you cannot slow down the publishers. They go too fast and the data is too important. So we have the ability to do drop semantics. So I will read, and I have a ring buffer in memory where if I read fast enough, everything is good. If I stop reading fast enough, then I start dropping messages. And of course, I can get a report for how many messages have been dropped to me because I'm too slow. But that was really important, and that allows our developers to connect processes that may be broken, that may pause, that they may debug. If you can imagine running a process and you drop into a debugger and it stops reading messages, it would be really horrible if that took production down. Configurable backlog of messages, so I only want, in our case, I only want 30 million messages in the queue, no more. Like bad things have happened there. So most tragic distributed systems problems in big architectures happen because people don't bound their queue sizes or their timeouts, right? A queue doesn't mean that you will get all of your data forever, right? If you can imagine using an asynchronous queue for something that sends 10,000 messages a second, and you have an outage that's 10 hours long, like you probably don't even want to keep all of that data. So we also have transient and permanent attachments. We have memory and file backs, so by default most of our stuff stays in memory, we just keep it in memory. And then we can saturate a little over 30 gigabits on a single box with this. So the idea of distributing it out in a cluster is not as necessary as you would think. It's a lot of messages per second. So if you want to, that's written in C, as God intended software to be written, and assembly, and it's open source, so if you want to play with FQ, you should do that. So we pose the same questions. We have to be able to safely convert this over. So unlike a database where you need to write to both places and you can choose to read from one of them, in a message queue it's very hard to just choose to read from one of them. So there's slightly different approaches here. In message queues, because you don't have to store anything in a message queue, really, I can publish to one message queue and then flip to another one to see if it works and then flip back. And there's no fallback. It's not complicated. I don't lose data forever because my data is transient anyway. So it's an easier problem, but the question is how to make it safe. And the answer is that if you can make your systems tolerant of duplicate messages, you solve the whole problem entirely. So what we did is we dictated that every consumer of the message queue is responsible for deduplicating messages that they receive. So our delivery semantics are at least once. And FQ will really never deliver you a message more than once. But if we have rabbit and queue and 2 FQs and we're publishing to all 3, and you're subscribing to all 3, one thing is you're going to get the message. Second thing is you're probably going to get 3 messages. So the important thing is it's an axiom of computing. There's only 3 numbers in computer science, 0, 1, and infinity. So once you've solved the 2 problem or the 3 problem, you've kind of solved all of the numbers between that and infinity. So we have a special case here. The question is how do you deduplicate messages at 4 million messages a second and keep that fast enough? And the answer to that is that we timestamp every message at the source. So every message has a Unix timestamp on it. And we only need 10 seconds of data. So what we do is we store 20 deduplication hash tables in memory. And as the messages come in, we make sure that it's within 20 seconds old. And we hash the message contents. And then we store a hash entry for that message in that bucket, that second bucket. So we modulo by 20 here. And we have a hash table in this bucket that has every single message we've seen in this time slot. And that's order 1 insertion and order 1 checking. So if I have a new message come in, I can go look in whichever bucket it's supposed to be, in bucket 2, I hash the message, I check to see if it's there, and then I can drop it, because I've seen it already, or I can add it if I haven't. The beauty of that system is that there's no chained linked lists or LRUs that need to be created for that, because when this bucket gets too old, it wraps, and I just delete the whole hash table, because that hash table is now too old. So we insert hash elements, and we check for hash elements existence, but we never delete hash elements, we just delete the whole hash table. So this makes it actually scale very, very well computationally. So if you have timestamped messages, this is definitely the way to do that. And this is sort of what a failure looks like. No one cared, right? So this is some sort of bug where all of those messages started getting rejected out of one of our MQs, but they were listening to 2. So instead of clustering our message queues, like our rabbit message queues, we run 2 completely independent FQ instances, and everyone publishes to both of them, and everyone subscribes to both of them. So if one fails, you just start getting 1 copy instead of 2 copies of the message. And if you wanted 3, then you could do 3. And it makes it very easy for us to test our software. So when we release new versions of the FQD, the FQ broker, we can deploy a 3rd copy, and when it breaks and doesn't deliver messages correctly, and no one cares, because you have 2 known good copies. So that works very, very well. It allows a lot of flexibility in how you operate the system. And thank you. And yeah, that's kind of it. We have time for questions.
А почему не использовать React вместо вашей собственной базы данных? Очень похоже на React. Да, на React очень похоже. Почему бы не использовать React вместо нашего решения? Отвечу так. Те типы данных, которых мы используем для того, чтобы хранить данные временных серий, мы должны... Дело в том, что React не меняет значение ключа, потому что наша серия данных, она постоянно растет, и мы не храним отдельные ключи, потому что у нас получается единый ключ на всю очередь сообщений. Здравствуйте, спасибо за презентацию. У меня вопрос про хэш-ринг, про хэш-кольцо, которое вы описывали. А что происходит в том случае, когда у вас не просто отказ, а операция switch-off, switch-on, выключение-включение? И когда осуществляется фейловер, в таком случае что? Дело в том, что кольцо не перераспределяет ключи автоматически. Когда отказывает какой-либо из узлов, у вас остается две копии. При записи, если осуществляется сбой, узлы, ноды определяют, насколько они свежи, скажем так. Так что выбирается для чтения самый свежий, а не тот, который отстает, например, на 30 секунд. Так что каждый нод ведет журнал, и когда система снова поднимается, туда поступают эти транзакции, и такой подход работает достаточно надежно. Спасибо, понятно.